All right, so in this next one, this is definitely one of those cases where we have a function, right, or we have an equation, capital R is equal to x times p, and then we're told that 2x plus 3p is equal to 12. This is one of those classic optimization problems where we're going to optimize something and we're based off of a constraint. Probably the easiest way to know which one's the constraint and which one's not is just the number of variables. You'll notice that in this equation there's 3 variables. There's r, x, and p. And in this one there's only 2 variables, x and p. So that's probably a good indication of what the constraint that's given and then the function that will eventually be maximized. As a matter of fact, you do see me asking to maximize r, right? Maximize r. So here's the thing that needs to be maximized, and here's the thing that needs to be constrained by. What it also is an example, even though I'm not using the word, this is revenue. So let me explain this guy here, and then we'll talk about this guy there. Revenue, right, in all practical purposes, revenue is the number of units that I have times the price that we sell them for. That's how much money we come. So if my number of units is X and my price is P, then the revenue I make is X times P. And so that's literally what revenue is. So revenue is the number of units that I sell times the price. So for example, if we're selling, let's say, some books and I'm selling them at $10 a pop, then the revenue that I have coming in, right, would be $10 times the number of books that I have. So if I had 10 books, we'd bring in $100. Of course, that's not profit because there was a cost in producing those books. So money coming in, revenue, minus the cost would give me my total profit. We're just talking about money coming in. Now, so that explains that guy. This guy right here is actually our demand equation. As you guys classically know, the price, right, under normal circumstances, right, if this is the price and this is X, the higher the price is, the lower the amount of things will be demanded. The lower the price goes, the higher the demand. So a classic demand curve looks like a line that's on its way down, indicating again that if I flood the market with a bunch of units, the price of the objects will go down. If I don't flood the market with a bunch of units, like if I only produce one Lamborghini, right, the price of that Lamborghini is going to be really high. And that's basically what that is in terms of a revenue situation. So this is our demand equation. It's our constraint. And what we're going to slowly do here is maximize our revenue. So here's how we're going to do it. The first thing we got to do is find R as a function of X. Right now, R depends on X and P. So what I need to do is find P of X, right? What is P in terms of X? And then it's a simple substitution. Well, what I'm going to do is go take my demand equation and basically solve it for P. So subtract 2x from both sides. We get 3p equals negative x plus 12. If we divide by 3, we get that p is negative 2/3 x plus 4. So I can now come to my revenue function, right, which is x times p. X is still x, but p is negative 2/3 x plus 4. And so when all is said and done, our revenue function is negative 2/3 x squared plus 4x. So for this situation, we've just built the function that we're going to maximize. And we did it by using the constraint to go from something that depends on 2 things to a function that depends on just 1 thing. And we know how to handle this. This is our classic f of x situation. The good news too, it's also a parabola, right? And the leading coefficient is negative, so we do know that this graph is a parabola heading down, so there will be a maximum out. So that's why the next sentence makes sense. What values of x will maximize my revenue? Well, again, all we need to do is find the x coordinate, right? I think we called that h and k in the past. We need to find the x coordinate where that vertex is at. So what do we know about h? It's negative b over 2a. And so for my example, we have negative 4 and 2, and my a is negative 2/3. So on the bottom, a negative divided by negative is a positive. So we have 4. And on the bottom, if we multiply, we get 4/3. Alrighty? Multiplying by reciprocal, the 4's cancel out, and we're left with 3. So h is equal to 3. That's the x value that's going to produce a maximum revenue. All right, so x is equal to 3. What is the maximum amount? Well, again, to find the vertex, to find the k value, k is my revenue function evaluated at that x coordinate. So we got negative 2/3, 3 squared, plus 4 times 3. And I think that will become negative 2/3. 3 squared is 9, plus 12. 3 goes into 9 3 times. We have a negative 6 plus 12. We get 6. So k is equal to 6. So whatever this function looks like, it has its maximum value at 3, and it's occurs at 3, and the output is 6. So for this revenue situation, our vertex is at 3, 6. 3 items needed to produce a maximum revenue of 6. Okay, and then one last question that we can also answer because of everything going on is we can actually figure out what is the price, right? What is P that will maximize that revenue? Well, we already know that's happening at x equals to 3, right? That is the value of x that makes my revenue the profit, or excuse me, the maximum. And right here we were told, or we found out, that P is 2/3 x plus 4. So to find the price that maximizes the revenue, all I got to do is substitute the value of x where that all happens. And so in this case, we get negative 2/3 times 3 plus 4. The 3's will cancel out, and it looks like P is equal to 2. So when P is 2, we maximize the revenue, right? When X is 3, we maximize the revenue, and that maximum revenue is 6. And you can do a really quick check because we know, right, that R is X times P. When X is 3 and P is 2, right, what we get is that maximized revenue of 6. So everything comes together, right? Our formula for revenue with our constraint equation that we have, it all matches up. Okay, so another classic case where we're given something we need to maximize based off of a constraint. What we do is we use that constraint to solve for one of the variables, substitute that in, and we now have a function like we're used to be working with, in this case R of x. And then now that it's a quadratic, finding the maximum and minimum is just simply finding the vertex. Okay, and then the other question was kind of more to the story, but it's something we can add to since I have relationships between x, p, and capital R. So everything working together as it should. All right, so a lot going on in these problems. Make sure you're working. That's why we're just going to focus on 2 major sections this week because as you can see, there's a lot going on. One more revenue example coming up. We'll do that in another video coming soon.